Have you ever really thought about our power grid? I mean, it is a massive, continent-spanning machine, and keeping that whole thing in balance, well, it's one of the biggest computational challenges on the entire planet. So today, we're going to peel back the curtain and look at the incredible math that keeps your lights on. Just look at this map. This isn't just a bunch of lines and dots. It's a giant web of interconnected math problems. Every single generator, every transmission line, every factory and home, they're all variables in a massive equation. To keep the grid from, collapsing, engineers have to know exactly what's happening everywhere, all at the same time. And that gets us to the core challenge here, the load flow problem. Yup, the load flow problem. You might also hear it called the power flow problem. At its heart, it's all about trying to solve a huge set of really tangled, nonlinear equations. We're not talking about high school algebra here. You can't just solve for one thing at a time, because every part of the grid affects every other part. You change one tiny thing over here, and a ripple effect shoots across the entire system. So how in the world do you solve a problem that seems, well, unsolvable? You guess, you check, and you guess again. It's called iteration. For decades, engineers have relied on two classic methods to inch closer and closer to the right answer. So let's meet our two main contenders. First up, we've got the Gauss-Seidel method. You can think of this one as the slow and steady workhorse. It tackles the problem one point at a time, what engineers call a bus. A bus is basically just a major intersection on the electrical highway. So this method calculates the voltage for the first intersection, and then, and this is key, it immediately uses that brand new, better value to help solve for the next one, and on down the line. So what's a good way to picture this? Okay, imagine you're on a hill, but it's completely covered in fog, and you're trying to find the very bottom. With Gauss-Seidel, you can't see anything. You just take one small step, feel around, check your new position, and then take another small step from there. You'll get to the bottom eventually, for sure, but it might take a while. And that brings us to contender number 2, the Newton-Raphson method. This one is way more sophisticated. It's the high-performance option. Instead of taking those small, plodding steps, it uses a really powerful mathematical tool. It's called the Jacobian matrix to take much bigger, smarter leaps toward the answer. So what is this Jacobian thing? Don't worry, you don't need to know the calculus behind it, just the concept. If Gauss-Seidel was like walking in that fog, using Newton-Raphson is like suddenly having a detailed topographical map of the entire hill. The Jacobian shows you the slope everywhere, so you can instantly see the steepest, most direct path to get downhill to the solution. The whole process is actually pretty elegant. You start with a really simple guess. Engineers call it a flat start, basically just assuming everything is normal. Then you check how wrong that guess is. That's your mismatch or your error. Then you look at your Jacobian map to find the best way to fix your guess. You take a big, calculated step in that direction, and then you just repeat. After just a few of these steps, you're incredibly close to the exact right answer. Okay, so now we have our two methods. One is simple but kind of slow, and the other is super fast but way more complex. Let's put them head to head, because this is a classic engineering trade-off. All right, let's break this down. You've got Gauss-Seidel over here, the reliable snail. It's slow, sure, but it's simple, and it almost always gets to the finish line. Then you have Newton-Raphson, the cheetah. It's ridiculously fast. It has what's called quadratic convergence, which means the number of correct digits in your answer can literally double with every single step. But here's its weakness. If your first guess is way off, it can get totally confused and just fail. It's that classic choice. Do you want guaranteed slow progress, or do you want risky, high-speed performance? So if one's too slow and the other can be unstable, what do engineers actually use in the real world? Well, turns out they came up with an incredibly clever compromise that kind of gets you the best of both worlds. And it's all built on a really fascinating quirk of physics. See, in high-voltage systems, a really convenient thing happens. Think of electricity as having two main components. You've got real power, that's the stuff that does the actual work, like spinning a motor. Then you have reactive power, which is kind of like the pressure in a hose that keeps the voltage stable so the real power can flow. Well, engineers discovered that real power flow is mostly tied to the angle of the voltage, while reactive power flow is mostly tied to the magnitude or the level of the voltage. And that one insight led to something called the fast decoupled method. It's basically a version of Newton-Raphson, but it makes this one brilliant simplification. It just decides to ignore the weaker connections, like how the work energy affects the voltage pressure. By focusing only on the strong relationships, the math becomes so much simpler and faster.
The effect this has on a big system like this is just profound. Instead of calculating that full, complicated topographical map from Newton-Raphson, this decoupled method lets us basically break the problem into two much simpler puzzles. And we can solve those two puzzles way, way faster. It's a fantastic piece of engineering that just dramatically speeds up how we analyze these complex grids.
So we've talked a lot about the how. We've gotten into the weeds of the math. But what's the so what? Why does a faster, more reliable load flow calculation actually matter to you and me?
Because pretty much every important analysis of the grid depends on it. You want to plan where to build a new power line? You need load flow. You want to study how to stop a cascading blackout? That starts with a load flow calculation. You want to know what happens if a huge transmission line gets knocked out by a storm? That's called contingency analysis, and guess what its first step is? Load flow. It is the absolute bedrock of modern grid operations.
You know, this quote here really says it all. You just can't analyze how stable or secure or even how economical the grid is without first getting a solid snapshot of what it's doing right now. And that snapshot, that is the load flow solution. And speed really, really matters. Get this number, 8,760. That's how many hours there are in a year. To plan for a whole year of grid operations, planners might have to run a separate load flow study for every single hour. When you're running that many calculations, the speed difference we've been talking about isn't just academic. It's the difference between being prepared and completely flying blind. And that kind of leaves us with one last big thought. These incredibly powerful methods were designed for a grid with big, predictable power plants. But what happens now when you add millions of solar panels, thousands of wind turbines, and a growing fleet of electric cars, all changing their output from second to second? The power flow problem is only getting harder. And the real question for the next generation of engineers is, are these classic tools going to be enough to handle the grid of tomorrow?